derivatives is called the Jacobian matrix. And when you're faced with a nonlinear system of ODEs, what do? Linearize it. You linearize it about each equilibrium point. And then in a saddle, when you have a saddle at an equilibrium point, the straight line solution that goes towards the origin is called the blank separatrix. Stable. And the one that goes away is called unstable. Okay, so today we're going to formalize and shorten the process of linearizing a nonlinear system about an equilibrium point. So if you were here last class, the process was relatively painful. I think so, if they're not in your folder. One more. Okay, so we have this nonlinear system. X prime is some stuff with x's and y's in it, and y prime is some stuff with x's and y's in it. You need a packet also? Oh yeah, there were 2 lessons in the last packet that I handed out. Okay. So you could think of, if x prime is some stuff with x's and y's in it, you could write it as a function of 2 variables, a function of x and y. Just means it's a formula. It's just some sort of formula with x's and y's in it. And then the y prime is also some formula with x's and y's in it. So we'll just, instead of writing a specific formula when we're trying to generalize the process, we'll call it f of xy and g of xy. So let's say that x naught, y naught is the equilibrium point for the system, and we want to understand the behavior of the system near x naught, y naught. So we want to linearize around that equilibrium point. So the process we learned from last class is first, we might need to introduce new variables to shift the whole system so that the equilibrium point's at the origin. And the purpose of doing that is that you can throw away all higher order terms if your equilibrium point is the origin, because when you're really close to 0, a higher order term like x squared, y squared, xy, those things are taking really small things and multiplying them together, and they get even smaller. So you can throw them away if your equilibrium point is the origin. So the first step was to move everything to the origin. Then we have to substitute our new variables into the system. Then if you have nonlinear terms that aren't polynomials, you use a Taylor polynomial to replace them. So I don't think many of you got to the second example where you had to do that in class. So in the second example, the nonlinear term was sine of x. And sine of x, when you're really close to 0, is not negligible in size. Right? You can't just throw it away, because when you're near 0, the sine of x isn't closer to 0 than a linear term. So instead, you replace sine of x with its Taylor series and then throw away the higher order terms. All right, so today's shortcut is much quicker. You calculate the Jacobian matrix of partial derivatives. So we've got 2 functions. Both are functions of x and y. It's just the right-hand side of your 2 differential equations. Take the partial of f with respect to x and the partial of f with respect to y. Those make the top row of your matrix. And then the partial of g with respect to x and the partial of g with respect to y. Those make the second row. Then plug your equilibrium point, x naught, y naught, into each of those partial derivatives in the Jacobian matrix, and done. That's the linearized, that is the matrix A in the linearized system, y prime equals ay, right? And your matrix of partial derivatives evaluated at your equilibrium point is your A. So much, much faster than the process we did last class. It comes from exactly the process we did last class. If you Follow the process from last class on a generic f of xy, g of xy, equilibrium point, x naught, y naught. Go through the whole thing that we did last class generically. This is what you end up with, the matrix of partial derivatives. So I'm not going to derive the whole thing for you because you did all that work last class. We'll just do an example. All right, so remember, the purpose of the linearized system is that we can look at the solutions to the whole nonlinear system near each equilibrium point, and then we can try to guess or stitch together a phase portrait of the entire nonlinearized system by trying to connect the little mini phase portraits we have at each equilibrium point. Okay, so I have a nonlinear system here. In this first equation, x prime equals negative 2x plus 2x squared, what makes it nonlinear? The 2x squared, yeah. And in the next one, the 3x squared makes it nonlinear. All right, so first I need to find the equilibrium points. So we do that by taking our two equations and setting them to 0. So this first equation is dependent only on x, so I should be able to just solve it outright. I can factor out a negative 2x, and I'd be left with 1 minus x. And then either x would have to be 0 or x has to be 1. So I have two possibilities for x. I have to take each of those possibilities, plug them into my other equation, and get the y that corresponds with it. So when x equals 0, we end up with y equals 0. So I have an equilibrium point at 0, 0. When x is 0, y is 0. All right, and then I'm going to plug in x equals 1 into this equation. And again, you get y is 0. Because you get a negative 3 and a positive 3, those cancel. So we get y equals 0 again. So my two equilibrium points are 0, 0, and when x was 1, y was 0 again. So two equilibrium points, 0, 0, and 1, 0. Okay so far? All right, so now we begin the process of trying to linearize the system about each of these equilibrium points. So first I have to come up with the Jacobian matrix. So maybe I'll rewrite the system here. Negative 2x plus 2x squared. And y prime is negative 3x plus y plus 3x squared. Okay, so there's my system, which means my Jacobian matrix, 2 by 2 matrix full of partial derivatives. So I take the partial of f with respect to x. So this one, this is f of xy, right? And this one is g of xy. So looking at the x prime equation, what's the partial of 2x plus 2, negative 2x plus 2x squared with respect to x? Negative 2 plus 4x. And what is the partial of that same equation with respect to y? 0. Yeah, there are no y's in there. You treat everything else as a constant, so its partial is 0. All right, looking at the y prime equation, what is its partial with respect to x? Negative 3 plus 6x. Treat the y as a constant when you're taking the derivative with respect to x. And then the derivative with respect to y, 1. Treat everything with an x as a constant. The derivative of the y is just a 1. All right, so that's our Jacobian matrix. And then I have to evaluate that matrix at each equilibrium point. So my Jacobian matrix evaluated at the point 0, 0, my first equilibrium point. So I'm just plugging in 0 for x and 0 for y. So I have negative 2, 0, negative 3, 1. That is the coefficient matrix for my linearized system at 0, 0. And then how do I figure out what the phase portrait looks like? Just get the eigenvalues, yep. So I would do -2 minus lambda times 1 minus lambda minus 0 equals 0. And I get lambda would be -2 or +1. Yep, I plugged in the point 0, 0, 0 for x, 0 for y. So what kind of phase portrait do I have at 0, 0? A saddle. 1 positive, 1 negative eigenvalue. We have a saddle. All right, if I'm going to try to draw it, what do I need to be able to draw this saddle? I need the eigenvectors, yeah. So I'm going to run out of room here. I'll go on to the next page to do the other equilibrium point. So I just got to solve this equation, AV equals lambda V, to get the eigenvectors, and I got to do that twice, once for -2, once for 1. So my A is -2, 0, -3, 1. Vector is, don't know, that's what I'm looking for. Lambda is -2. So I'm just looking for any vector x, y that would make this equation true. There's an infinite number of them. Yeah, so if I look at this, I do -2, 0 dotted with x, y, and I get -2x plus 0y equals -2x. That is true no matter what x I pick. That gives me nothing. So I do the other one, and I have -3x plus y has to equal -2y. So yeah, so 3y equals 3x. So y equals x. So my eigenvector, the easiest one would be 1, 1. Good. And then I just do the same thing again, but then I replace the -2 with a 1. And I'll solve the same set of equations, and I get -2x has to equal x, tells me nothing. No, it's not true. Let's write it down. -2x has to equal x. What x value makes that true? Yeah. -1/2. If I put a -1/2 in for x, I get 1 on the left and -1/2 on the right. 0. X equals 0. So I'll get the same, either I'll get the same information from the other equation or I'll get no information from the other equation. So give me an eigenvector with x equal to 0. 0, 1. All right, so I'm going to sketch this saddle before I move on to the other equilibrium point. And in part C, I'm trying to stitch together my 2 phase portraits. I'm going to have a small phase portrait at each equilibrium point. So I'll do the one at 0, 0 now. Okay, so at 0, 0, I have a saddle. And one of my eigenvectors was 1, 1. Line y equals x. And the other one is x equals 0. So 0, 1 would point straight up like that. Now the one that points straight up and down, does it point at the origin or away from the origin? Away, because it was the one that was lambda equals 1. It was the positive eigenvalue. So that one points away. This other one was for lambda equals -2, so that points towards the origin. And I'm just going to leave out the saddle parts for now. I'll just put in the straight line solutions, and I'll just remember that it's a saddle. It might help me when I'm trying to connect it to my other equilibrium point. All right, so my other equilibrium point was where? 1, 0. So I'm just going to put it way over here so that we have plenty of room to draw it. at 1, 0. So now I have to do the whole linearization process at 1, 0. So I figure out what that looks like. So my Jacobian was -2 plus 4x. Yeah, I can't remember. -3 plus 6x, 0, and 1. Okay, so my second equilibrium point was at 1, 0. So now I'm plugging in 1 for x and 0 for y. There aren't any y's, but if there were, I'd make them 0. So if I put in a 1 for x, -2 plus 4 is +2. -3 plus 6 is +3. 0, 1. So there's the coefficient matrix for my linearized system at 1, 0. Find the eigenvalues. 2 minus lambda times 1 minus lambda minus 0 equals 0. And I get eigenvalues lambda equals 2 and 1. So what kind of equilibrium point do I have? A source. Both positive eigenvalues. I have a source. Okay, so I have to figure out what the straight line solutions are, and that will determine what the phase portrait looks like. So I need the eigenvectors. So I solve A times some unknown vector xy equals lambda. We'll start with the 2 times xy. So this first equation says 2x equals 2x. That tells me nothing. So my other one is 3x plus y equals 2y. So this says y equals 3x. So an eigenvector would be 1, 3. Make 1 x1, y would be 3. Then I just solve the same equation, but replace the lambda with a 1. So 2x has to equal x. If you look at the first row. And that only happens when x is 0. So my eigenvector would be any 0, comma anything. I've got 1, 3, and 0, 1 as my eigenvectors. And 1, 3, that went with lambda equals 2. Just got to remember which of these is which. This went with lambda equals 1. All right, so on my phase plane, at 1, 0, I have a source, and one of my straight line solutions is 1, 3. So I would go over 1, up 3, and my general direction over 1, up 3. It's pretty steep. And everything's going out because it's a source. And then my other one was 0, 1, which means it's going to point up. Right, because there's no y value. So y can vary, just x has to be 0. I'm putting it at the equilibrium point 1, 0. Right, that is the point we just linearized around. All right, so now I have to try to connect these things. So I got to remember how to draw. I know the saddle is pretty easy, the way you draw on the rest of the phase portrait. For a source, you got to remember the 1, 3 that went with lambda equals 2, and this one went with lambda equals 1. The way you draw the phase portrait for a source is that the bigger lambda, or the lambda that's further from 0, is always considered the faster eigendirection. So it's going to come in parallel to that and tangent to the other, or leave parallel to that and come out tangent to the other. So it's going to be like tangent to this one and parallel to the fast one. So tangent to the straight one, they're both straight, I don't know why I said that. Tangent to the slow one, parallel to the fast one. The slow one is the one that's eigenvalue is closer to 0. And then in here, I get to be tangent and parallel, so it's something like this. And then tangent to the slow one, parallel to the fast one. Something like that. The 1, 3. What about it? No. No, different lines, yeah. All right, so now I need to kind of stitch together how is this going to work. So generally you take your separatrix or your separatrices, which are the two straight line solutions in a saddle, and you can connect them to the other equilibrium solution, right? So here's an equilibrium solution at 1, 0, and it's a source. So everything is going to leave out of there. So it's going to leave tangent to the slower one. So it's going to leave tangent to this vertical eigenvector, and then it's going to turn around, right? Because that's what the phase portrait looks like near 1, 0. So it's going to turn around, but there's going to be one. There's going to be exactly one in here that tries to leave. It gets turned around, and instead of coming down parallel to the fast eigenvector, it's going to get captured by the other equilibrium point. So you're going to have one special solution that leaves here. It tries to do what it's supposed to turn around, but it got too far away from this equilibrium point, and it's going to get captured by this saddle separatrix. Only one that will connect to the separatrix, yeah, but others will the ones below this will sort of join the saddle part, right? So anything that comes out below that will join the saddle of this, of the other one. And we kind of can see how they connect. Yeah, the ones above it, we're going to do the other saddle. So if they come out above the green separatrix, they're going to follow this pattern. Why? So as soon as it gets, I mean, this is very qualitative, so it's you can't say which one, right? But at some point, these solution curves are gonna meander far enough away from this equilibrium point that they're not going to be governed by the behavior that we think should happen near this equilibrium point, because we linearized. The linearization is only good in some small window around the equilibrium point. So as soon as it gets far enough away, it's no longer governed by the linearization that we did, and it's going to get captured by the other one. So it'll get sort of sucked into the other equilibrium point, or it might just head off towards infinity, like these guys over here to the right of the second equilibrium point. They're just going to keep doing whatever, right? They're just going to keep going forever away from the equilibrium point. They're never going to get captured by the other one because they're moving in the other direction. Like that. No, also you can't cross solution curves in the phase plane. So I have one drawn here that shouldn't be because it's crossing those two blue ones, right? Yeah, so you can't cross the separatrix, or you can't jump over a straight line solution. It's that uniqueness thing from chapter 1. You can't cross solutions. So yeah, this green line connects to the saddle that's coming in, and we call that the separatrix. You have qualitatively different kinds of solutions below and above the separatrix. All the way down here? I think they're all going to approach this vertical solution asymptotically. Yeah. No, they won't turn around again. Yeah. And I mean, it's really hard to know if a nonlinear system has, it might have unpredictable behavior when you get far away from these equilibrium points. This is like one small tool we have to attack a nonlinear system. So here I have a numerically generated phase portrait. We've got the source here and the saddle here, and you can see how they connect. And if you zoom in on the source, it looks just like a source that we would have drawn in chapter 3. And if you zoom in on the saddle, it looks just like a saddle we would have drawn in chapter 3. And then you just try to like stitch them together, and it's part art, right? Like you can't know exactly how they fit together because it's a nonlinear system. Yeah. All right, so I already used the terms here, but in a saddle, there are 4 straight line solutions. Well, 2, but you can break them in half at the origin. Right? That tend towards or away from the equilibrium point, and each of those is called a separatrix. The 2 separatrices that tend towards the equilibrium are called stable, and the 2 that go away are called unstable. So just one more time, I had the source connecting to the separatrix, right? This is a special curve in the phase plane, and all the solutions above it have qualitatively different behavior than the solutions below it. They're captured by the saddle equilibrium point in a different way. So many of your questions are answered in this number 7 here. Sometimes linearization just doesn't give us good information about the behavior of a nonlinear system. So for example, if you linearize a system at a particular equilibrium point and you get a center, there's like no way to stitch a center to something else, right? Because the center just keeps going around and around and around. So how does it connect to another equilibrium point? So typically, when a linearization gives you a center, the true behavior is likely a spiral source or a spiral sink, and it's just that when you threw away the nonlinear terms, they actually made a difference in what happens near that equilibrium point. And they were large enough to change the behavior of the solution. So this is a tool, but it's a pretty primitive tool, and it's the only tool we're going to learn for nonlinear systems. All right, you try some.